Hello, my name is Juhyun Song, and I'm a senior undergraduate student majoring in electrical engineering at Korea University and the president of QUIC. Today, I'll be giving an introductory seminar on quantum key distribution. This talk is aimed at those who are completely new to this topic, so I'll walk you through the fundamentals step by step. In this seminar, we will begin by reviewing classical communication. Then we'll explore the core principle of quantum key distribution systems, how QKD protocols are categorized, and finally take a closer look at two representative protocols, BB84 and E91. Communication. Imagine Alice wants to send a message to Bob. In our modern digital world, we first convert the message into binary bits and then transmit it over some communication channel. But what happens if someone tries to intercept the communication? Let's say an eavesdropper, Eve, secretly gets in the middle of the communication between Alice and Bob. This kind of situation is known as a man-in-the-middle attack. Eve can pretend to be Bob when talking to Alice and pretend to be Alice when talking to Bob. In this way, she can intercept, read, and even alter the message without either side knowing. To prevent this kind of attack, we use encryption. Instead of sending a raw message, Alice encrypts it using a secret key so that only Bob, who has the correct key, can decrypt and read the message. This use of encryption allows for secure communication, even over potentially insecure channels. Then how can we share the key in the first place? There are mainly two types of key distribution, symmetric and asymmetric. In symmetric distribution, both parties share the same secret key in advance. In contrast, public key distribution uses a pair of public and private keys. It allows anyone to encrypt a message using the public key, but only the holder of private key can decrypt this. Today, asymmetric methods like RSA are widely used. RSA is typically based on the mathematical difficulty of factoring large integers, and it's the dominant approach in modern communication systems. However, the security of RSA relies on the assumption that factoring large numbers is hard. But one of the most famous quantum algorithms, Shor's algorithm, has shown that factoring can be done much faster than any classical method. This creates a serious quantum risk. If powerful quantum computers become available, it could break the cryptographic system we use today. In response to this threat, two major approaches have emerged: quantum key distribution and post-quantum cryptography. In this seminar, we will focus on QKD, which achieves strong security based on the fundamental properties of quantum mechanics. Just to briefly mention post-quantum cryptography, despite the name, it has nothing to do with quantum physics. Instead, it aims to develop new classical algorithms based on even harder mathematical problems that are believed to secure against quantum attacks. So, what makes quantum key distribution fundamentally different from classical cryptography? The core idea is that QKD is secured by the laws of quantum physics. There are three important quantum principles to understand. First, the non-cloning theorem tells us that it is impossible to perfectly copy an unknown quantum state. This prevents an eavesdropper from making duplicate of the quantum signal. Second, superposition allows quantum qubits to exist in a combination of states, enabling more complex and flexible ways to encode information compared to classical bits. Third, entanglement creates strong correlation between particles, no matter how far apart they are. This property proposes a completely new paradigm for secure communication. Let's look more deeply through no cloning theorem. No cloning theorem state that there is no unitary operation that can clone an arbitrary unknown quantum state. So let psi and phi be two arbitrary pure quantum states. we're gonna assume that there exists a cloning machine. So here, cat E is the blank state that is supposed to be transformed into a copy of the input. So if we apply the unitary operator here, this cat E should be changed into the input, which is psi here, and which is cat phi here. And just note that cat E is normalized, so the inner product of itself is just 1. If we make the bra psi cat phi and inner product of cat psi and cat phi and inner product of the E itself should change into bra psi cat phi because E is normalized and its inner product is 1. And it can also be written as bra psi tensor E and cat phi tensor E. So this is like the same expression as this one. If we apply unitary operator here, then this side of the bright size has to change like this, so we can get the psi tensor psi here. And same thing happens to the cat size, so we can get phi tensor phi here. And this eventually goes to the bra psi cat phi squared. And just note that if we apply unitary here, it's the same thing as applying unitary operator here. And applying unitary operator here would become psi cat bra psi cat phi, and it has to be equals to its squared. But this final formula shows that it's the contradiction of our assumption. Since only 0 or 1 is possible here, that means orthogonal or identical states can be cloned. So this proves that perfect cloning is not possible in general. Now let's take a look at the basic structure of QKD systems. QKD protocols can be broadly categorized into 2 types: prepare and measure protocols and entanglement-based protocols. First, under prepare and measure protocols, we have discrete variable QKD or DVQKD. In this approach, photons are typically generated by a weak coherence light source, such as laser, not light, just weak coherent source, or sometimes by a single photon source. The security here comes from the no cloning theorem and the fact that any attempt by an eavesdropper, Eve, will introduce detectable errors. Some well-known example of DVQKD include BB84 and experience using polarization, phase, or plug-and-play setups, as well as DPS, DPTS, and COW protocols. Next, we have continuous variable QKD. In CVQKD, information is encoded in the quadrature, that is, the amplitude and the phase of the electromagnetic field. The security of CVQKD relies on quantum uncertainty in these continuous variables. Gaussian modulated coherence states and squid states are commonly used here. Finally, we also have the entanglement-based QKD, where entangled photon pairs are created as the source. By performing specific measurement on their respective photons, Alice and Bob can generate strongly correlated outcomes. Notable example includes the E91 and BBM92 protocols. Now let's take a closer look at the BB84 protocol. BB84 was proposed by Charles Bennett and Gilles Brissard in 1984. It was the first and remains the most well-known QKD protocol. In this protocol, a quantum channel is used to send qubits, while a classical channel is used to compare measurement bases. Qubits are encoded using 2 bases, typically the rectilinear basis and the diagonal basis. The protocol proceeds in the following steps. First, Alice prepares qubits in one of the 2 bases. Second, she sends them to Bob through a quantum channel. Next, Bob randomly chooses a basis to measure each qubit, And through a classical channel, Alice and Bob compare which bases they used and keep only the matching ones. This is called the basis of reconciliation. And next, they perform error checking to detect any potential eavesdropping by Eve. Finally, they carry out the process called key distillation to generate the final secret key. Now let's go over how BB84 protocol works using this example. For the quantum transmission, we use quantum channel, and public discussion, we use classical channel. Alice first generates random bits, which she wants to send to Bob. She then randomly chooses a basis, rectilinear or diagonal, for encoding each bit and send the corresponding photon. Bob, without knowing Alice's basis, also randomly pick a basis for each measurement. Since he sometimes picked the wrong basis, he won't always get the correct bit values. One important case to note is this 6 bit in the example. Here, Alice sent 1 using the rectilinear basis, meaning the photon was vertically polarized. However, Bob chose the diagonal basis. To measure it. Since the diagonal basis measurements can only distinguish between 45 degrees and 135-degree polarizations, the original vertical photon collapsed randomly into one of these two states. As the result, Bob gets either 0 or 1 with 50% probability. However, this randomness does not cause a problem in key generation. Through classical communication, Alice and Bob later compare their chosen bases and discard any cases where their bases do not match. This ensures that only correctly transmitted bits are used in the final key. After transmission, Bob publicly announced the bases he used with classical channel, but not the actual measurement results. Alice then compares these bases with ones she originally used and marks the matching cases. Only the bits where Alice and Bob used the same bases can be kept for final key. To check the potential eavesdropping, Bob randomly reveals some of the key bits, and Alice verifies that they match her own. If too many errors appear, they assume an eavesdropper might be interfering. Since the final key is very long, even small disturbance caused by Eve would introduce detectable errors. This means that Eve presence cannot go unnoticed. If Alice and Bob detect significant errors, they just discard the key and restart the key exchange process to ensure security. Though QKD using polarization state is easy to understand, it is not suitable for fiber transmission. This is because the polarization state is not maintained due to birefringence in the optical fiber. For this reason, polarization-based BB84, the protocol we previously discussed, is mostly used in free space communication. But when it comes to the fiber-based or wired channel, we typically use phase encoding protocols. Let's briefly look at the concept of phase modulation. You don't need to worry too much about the detailed equation. Instead, just focus on the example on the right. You can think of it simply as the method where we shift the phase by pi, depending on whether the beat is 0 or 1. So beat value 1 might correspond to cosine of omega t, and the beat value of 0 to cosine of omega t plus pi. That phase shift is how information is encoded. Just like polarization-based BB84 protocol, the phase-based BB84 also defines two bases. In the first basis, state 0 corresponds to 0, 0, 0 phase, and while state 1 corresponds to phi 0 phase. In the second basis, state 0 is pi over 2, 0, and state 1 is 3 pi over 2 and 0. Here we encode information by modulating the delayed pulse, which is separated using beam splitter. Since the separated poles originate from the same initial poles, they retain the same phase reference. This means that even though the absolute phase fluctuates as light propagates through the fiber, the relative phase difference remains unchanged. To create state 1, we apply a voltage of V pi to the phase modulator, which induces pi phase shift. Essentially, in this protocol, phase modulation itself determines the basis selection. After transmission through a quantum channel, Bob also has a delayed line interferometer and a phase modulator. By interfering the delayed pulse constructively and destructively, he can extract the bit information. For example, suppose Ellie sends state 0 using basis 1, and Bob also selects basis 1 for measurement. In this case, Ellie sends 0, 0, and for the short fiber path, it would be 0, 0, and for the delayed fiber path is also 0, 0. Since these pulses have identical phases, they will interfere constructively at single photon detector 1, producing a high signal at the constructive port, while interference at single photon detector 2 results in null signal at the destructive port. Therefore, Bob detects the photon as at SPD1 and correctly identify the bit as 0. It is important to note that the detection occurs based on the middle poles, which represent the interference result. Finally, compared to polarization-based BB84, the main difference is that here, the bit values are determined by phase difference instead of polarization states. However, the process of publicly revealing bases and calculating the error rate remain exactly the same. Even though QKD guarantees security in principle, the actual key obtained contains error due to device imperfections. Bit errors can be caused by things like phase drift or detector noise. So we apply an error correction process. One commonly used method is called cascade. In Cascade, the key is divided into blocks, and Ellis and Bob compare the parity of each block to identify and correct errors. These error correction techniques are classical, just like in conventional communication systems. But even after error correction, some information may still be leaked to Eve. That's why we use a second step called privacy amplification. This step also uses classical processing to reduce Eve's possible knowledge, typically by shortening the key through operation like exclusive OR. The final result is shorter but secure key. Now let's look at some common eavesdropping strategies that Eve might use in a QKD system. First, the beam splitting attack. This happens when the light source unintentionally emits multiple photons, like in weak laser pulses. Eve can tap a single portion of the signal using beam splitter. Although this may leak some information, the risk is low if privacy amplification is applied. Next, we have the intercept resent tech. Here, Eve intercepts and measures the quantum state, and then sends a fake one to Bob. Because of quantum uncertainty, her measurement introduces errors which can be detected by Ellis and Bob through increased bit error rates. So this is considered a moderate threat and is usually caught by error rate monitoring. Finally, the photon number splitting attack. Eve performs a photon number measurement and stores one photon if there are multi-photon poles while forwarding the rest. Later, after Alice and Bob discuss their bases, she measures the stored photon to extract the key. This is a serious threat, but it can be prevented using single photon sources or decoy state protocols. Now let's look at the E91 protocol proposed by Arthur Acker in 1991. This protocol uses entangled particles for quantum key distribution. Its security is verified through the violation of Bell's inequality, which is guaranteed by quantum non-locality. Here's how the protocol works. A central source sends entangled photon pairs to both Alice and Bob. Each of them randomly chooses a measurement direction. They then publicly share which basis they chose. Using some of the data, they test the CHSH form of Bell's inequality. If the result exceeds 2, it confirms that entanglement is preserved and Eve has not interfered. From the matching measurement outcomes, they extract a shared secret key. This method is fundamentally different from BB84 since the key is generated by correlation in entangled particles, not by the state preparation of single party. To understand the motivation behind E91 protocol, we first need to talk about the EPR paradox. This was proposed by Einstein, Podolsky, and Rosen in 1935. They pointed out that quantum mechanics predicts instantaneous correlation between entangled particles, even when they're far apart. Measuring one particle seems to instantly affect the other, which appear to violate what's known as local realism. Local realism includes two key assumptions. Locality, meaning no influence can travel faster than light. Realism, meaning physical properties exist independently of measurement. To explain quantum correlation while keeping this assumption, the idea of local hidden variable theory was introduced. But then John Bell came along and showed something remarkable. He proved that no physical theory of local hidden variable can reproduce all of the prediction of quantum mechanics. This is known as Bell's theorem. Bell also proposed an inequality that could be tested experimentally. If quantum mechanics is correct, a local hidden variable theories are wrong, then the inequality will be violated. This gave us a way to experimentally distinguish between the prediction of quantum physics and those of local realism. Let's now talk about CHSH inequality. You can think this similarly as the Bell's inequality. This is used in the E91 protocol to test for quantum entanglement. CHSH, named after Clauser, Horn, Shimony, Holtz. This inequality gives us a measurable statistical bound. If it is violated in an experiment, it means that nature cannot be explained by any theory based on local hidden variables. In the setup, Alice chooses between two measurement settings, which we'll call A and A prime, and Bob chooses between B and B prime. Their measurement results are either +1 or -1. The CHSH inequality denoted as S is defined as S equals the absolute value of expectation of A and B plus the expectation of A and B prime plus the expectation of A prime and B minus expectation of A prime and B prime. These expectation values can be written as integers over hidden variables lambda, weighted by a probability distribution rho of lambda. So E of AB equals to integral of rho of lambda times A of A lambda times B of B lambda integrated over lambda. If we expand the expression for S of lambda, we will see that in first term it contains B of B lambda plus B of B prime lambda. And for the second term, it contains B of B lambda minus B of B prime lambda. Since B only takes the value of +1 or -1, the result of each expression is either +2 or -2. Therefore, the absolute value of S of lambda is at most 2. Now, if we integrate this over all lambda using probability distribution rho of lambda, the result is the inequality S. So the CHSH expression is at most 2. So under any local hidden variable theory, the absolute value of S must be less than or equal to 2. But for the case of quantum theory, it's a little bit different. If we use the maximally entangled Bell state and carefully choose our measurement basis, we can achieve a maximum CHSH value of 2 times square root of 2. The calculation here shows this result step by step, and I encourage you to try to follow it yourself. Since the value clearly exceeds the classical bound of 2, it represents a violation of CHSH inequality and provides strong evidence that quantum mechanics cannot be explained by local hidden variable theory. Based on the previous equation, we can see how the E91 protocol uses CHSH inequality to determine whether the entanglement is preserved, and therefore whether eavesdropping has occurred. By assuming certain form of Eve intervention and working through the math, we can clearly distinguish between the presence of eavesdropping and no eavesdropping and possible eavesdropping. If you are interested in detail of the derivation, I recommend reading to this paper shown on the right. In the actual experiment showed in the centered graph, the measurement of CHSH value was around 2.5. Since this exceeds the classical limit of 2, it constitutes a violation of the CHSH inequality. And by Bell's theorem, it indicates that entanglement is preserved. Therefore, we conclude that no eavesdropper was present during the key exchange. Lastly, let's look at quantum relay system and finish the presentation. One of the main limitations of basic QKD system is transmission loss. Since they rely on single photon signals, these photons may be lost before reaching the receiver, especially over long distances. In classical communication systems, we typically solve this by using optical amplifiers or repeaters. However, in QKD, these cannot be used because single photon signals are easily buried in amplified spontaneous emission or lost during OEO conversion. Instead, quantum relay systems have been proposed. These take advantage of entanglement to extend the communication range. In the configuration shown here, 2 entanglement sources send photon pairs to Alice and Charlie and Bob to Charlie, respectively. Charlie then performs a Bell state measurement on the 2 photons he receives. Based on Charlie's results and their own measurements, Alice and Bob can generate a shared secret key, even though they never directly exchange photons. This way, QKD becomes possible over longer distances without amplifying or regenerating the quantum signal directly. To wrap up, these are the key points I hope you'll remember from today's talk: why QKD was proposed, the core principle it relies on, the types of QKD protocols, and the differences between BB84 and E91. Here's the references, and thank you for listening to my presentation.